Thank you very much for coming on a Friday afternoon. It's an honor and a pleasure to be in the Jones Seminars at the Thayer School of Engineering. I'm going to try to make this as informative and interesting for you as possible, and to try to persuade you that what used to be the realm of science fiction is increasingly becoming reality.
I think you want to swap that because that's your presenter.
Oh, okay. Let's see. Yep. How's that? Good. I have to go through the sort of mechanical way. What I'm going to, as I was saying, bring from the realm of science fiction into the realm of reality is the possibility that a nation's grid could be brought down, partially collapsed or totally collapsed through the use of a cyber attack. To look at this, we're going to focus on the U.S. and Canadian grid, otherwise the North American bulk power system. And I want you to look at this sort of from three perspectives. How could a cyber attack do this? What is it that makes the grid vulnerable to a cyber attack? Could that really happen? And if it did, how would it happen? And what would its impact be? First, on the operators of the grid, and second, on people trying to do their business deals, and hence concluding with talking about what kinds of preparations should we be making, especially should engineers be endeavoring to prepare for if they're going to help their companies and the grid itself recover from a serious disruption by cyber attack. Let me add one quick disclaimer. Because I teach at the U.S. Military Academy, I have to say this at the beginning of each talk. Nothing I say has been reviewed by or approved by or should be attributed to the U.S. Military Academy at West Point, Department of the Army, Department of Defense, or the U.S. government. Good. Now we've got that out of the way. Last night when I was doing my final preparations, I did a check on the internet to make sure nothing had happened during the day that would make me say that I ought to be mentioning this, and in fact something had. Admiral Michael S. Rogers, who is dual-hatted as both the director of the National Security Agency and the commander of the U.S. Cyber Command, was giving testimony before the Permanent Select Committee on Intelligence for the House. And the reports immediately started coming up about his testimony. The U.S. government thinks China could take down the grid. Wall Street Journal focused on the element that attacks to the grid he was predicting would start occurring within the near future and certainly by the end of the decade. I think it usually helps to hear what the man actually had to say. So I've excerpted a part for you. And let's see. And he's giving this under oath.
There are nation-states and groups out there that have the capability to do that. To enter our systems, enter those industrial control systems, and to shut down, forestall our ability to operate our basic infrastructure. Whether it's generating power across this nation, whether it's moving water and fuel, whether it's moving, some, I'll highlight those because those tend to be the biggest focus areas that we've seen. So once you're in the system and you're able to do that, it enables you to do things like, if I want to tell power trimmers to go offline and stop generating power, you can do that. If I wanted to segment the transmission system so that you could distribute the power that was coming out of the power stations, this would enable you to do that. It enables you to shut down very segmented, very...
Okay. What he's basically saying is cyber means can go in and interfere with, shut down parts of the grid. What he didn't say is that it could destroy parts of the grid. This was the unclassified part of the testimony. What I'm going to be talking to you about today is obviously not classified, but I'm going to be discussing not just merely turning off a generator or turning a transformer off as if you had pulled the plug, but damaging it so badly that it couldn't be used anymore, which would then raise the challenge of where do we get the replacement? Do we have it in inventory? Do we have to get it from offshore? So we're going to talk about a special kind of cyber attack that strikes at multiple nodes of a grid, that creates a disturbance that then ripples through the grid at the speed of light, that trips circuit breakers, the protective devices to prevent that kind of disturbance from getting into units that are only designed to handle a certain level of disturbance for a limited period of time, or they themselves are at risk of being damaged or of self-destructing, that can then disrupt that protective circuitry, destroy generators and high-voltage transformers, trigger cascading outages that are uncontrollable and unmanageable, and eventually causes the grid to break into islands. Now, what we mean by islands, in the blue lines are your normal area controlled by a balancing authority. So we're looking at 4 sections of an interconnection of the eastern grid. But within that now, when the grid breaks down, you see those black ovals. Let me give you such as here, or let's do this. Those two. Those are islands of the remaining power. When the rest of that grid goes down, those would remain standing temporarily. And you might have to do rolling outages to keep them stable so that the power generation and load were balanced. Some of these would then overlap several balancing authorities, and the problem is who has the authority to decide whether we're going to supply more power, drop load, balance it in a certain way, give it to certain customers and not others. And that's just the beginning of the kinds of challenges that the grid operators would have in what NERC, the North American Electric Reliability Corporation, NERC, calls a severe event. A severe event is the kind of event, whether it's a geomagnetic event or a cyber attack or a severe earthquake, so damages the grid that you cannot restore power and services to pre-event levels for months, if not years. So Hurricane Sandy was not a severe event. The Fukushima disaster and the earthquake that caused it and the tsunamis, that is a severe event. Okay? So, if you look at the chart that NERC has come up with, the severe event starts over here on the left. You notice there's efforts to mitigate the damage, but this is as far up as they can get restoration for a long period of time until they can get back to normal. This creates a new normal, and what would cause that? Well, if you have heavy transformers that have to be procured from offshore, and it will take 8 to 16 months to get them, that's what stops you from getting your service back to normal. It's not because the companies are lazy. It's because if this attack hit enough nodes, damaged enough equipment, there wouldn't be enough spares in the inventory. And remember, these are not small transformers like we have on our electric trains. These are these massive things, and many of them are custom built, as I'll explain as we go along. Now, this is a problem that NERC and its various participants have looked at for quite some time. This report came out in June 2010, where they started to approach the problem as a high-impact, low-frequency problem, like a meteor striking the Earth. Very low frequency, very high impact. The difference is, with cyber attacks, the low frequency factor is changing. It's becoming higher and higher frequency, and the impact is growing also. So NERC's view is that this kind of attack would have a maximum impact in minutes, that the effectiveness would be measured ultimately not only by how good the attack was, but how well prepared were the grid operators to respond initially. And the best analogy I can give to you is to think of a submarine, because grid operators, they're in a control room without windows. So is the commander and executive officer in a submarine. When they're submerged, they're not looking out windows like they did in 20,000 Leagues Under the Sea. They're looking at their displays as data comes in, and they only know what the data is telling them. And when they have a fire break out on board, their initial response to that fire usually determines whether the boat's going to be saved or not. The right initial response, and they get ahead of it. The wrong initial response, they get behind it. And if they're dealing with a coordinated cyber attack and they get inside their decision loop and the attackers are adapting as you're responding, and if they happen to know how you're going to respond, then they can frustrate or otherwise thwart that initial response. So the only way you can really cope with that is by thorough planning and preparation. That's going to ultimately be sort of the theme we want to get to at the end, because you as engineers, I think, have a role to play in that, in everything that you design and every kind of work that you do. So what questions do we need to approach this subject? I think you have to start out by understanding, how does the grid operate? How many of you are electrical engineers? Some. How many of you actually know how the bulk power system operates? Okay, so I'm not going to be boring you by giving you a brief tutorial on that. What happens to keep the grid operating reliably? Because, in truth, as magnificently reliable as it is, it's inherently unstable and can go off kilter in microseconds. What makes the grid vulnerable to damage by a cyber attack? Is that really possible? Because in spite of the fact that the Admiral said so, it's a nice thing for me to have as a sort of backup, and he's saying it under oath, so he's not fudging on that. Still, rather than just reading in the newspaper, our grid is vulnerable to cyber attack, I think you need a more granular understanding so that as engineers it appeals to you, because if you can't figure out or see how it works as an engineer, I think you'd be frustrated. Are cyber attacks to the grid really a credible threat? Again, when I wrote that, I didn't know that the Admiral was going to give that testimony yesterday. How will grid operators try to respond? And lastly, we'll run a scenario of two businesses trying to maintain their deals during the aftermath of a severe event. All right, how does the grid operate? The basic structure of the North American bulk power system is, by definition, distribution and transmission. Yes, there's generation and transmission. At the end, there's going to be distribution, but that's not part of the bulk power system. It's not regulated by FERC and NERC, which creates its own cybersecurity problems that we'll have to put off to another day. But as you look at the grid, there's a western interconnection. Think of that as one big grid island. There's the eastern interconnection, another big grid island. They are weakly connected by a few links. Then, of course, up in the north, the Quebec interconnection. And notice that the eastern and western both extend up into Canadian provinces. So the fact that there's that border there doesn't mean that the grid stops at the border. And then, of course, Texas gets its own, which is barely connected to the others. Okay, what's the basic structure inside each of those interconnections? Well, starting on the left, we have generation stations. That's where your power is generated. That power then goes out to a transformer. The purpose of that transformer is it takes already high voltage current, steps it up to very high voltage so that you can send it thousands of miles down the wire and still have it be at a decent voltage and power at the other end. At the other end, you then have a series of substations, not just one as the diagram is showing, that step it down for various customers. Some customers, heavy factories, they're going to require a higher voltage. Others, at households, they're going to want it stepped down to the stuff we're used to in the wall. So that's your basic overview: generation, transmission, distribution. And you heard the Admiral refer to interfering with the generation, interfering with the transmission. Undoubtedly, he's looked at this diagram too, I'm sure, because it's a very popular one that NERC has put out. Now, what does generation really involve? Power plants convert to electrical energy the energy that comes from a variety of sources. And of course, it depends on which sources and resources your country has. Coal, of course, is one. Natural gas, geothermal, hydropower, solar, and of course, nuclear. Now, from all of these, when it's generated, as I said, it comes out in voltage. It's three-phase alternating current, and that's why you saw in those diagrams three wires. They, in fact, all of these go out in three wires into the next system. So there's your three wires going into that step-up transformer, three at the other end, until it gets distributed. That's just the basic way it operates. Okay, what keeps it operating reliably? On one side, reliability is one of the most important things as long as it's being done safely. The other side is the fact that it's a very fragile system. It only operates if you keep it within manageable conditions, which the grid has both been designed and redesigned to keep refining as we develop it further. Disturbances, losses of, or any violation of those conditions, if you don't stop them quickly, they travel so rapidly they could cause damage if there weren't protective devices keeping that disturbance from getting in full force to various devices. And in fact, the grid is designed with sort of three basic subsystems throughout. One are protective circuitries, like circuit breakers and relays. The second, monitoring circuitries, your SCADA systems, your phasor, synchrophase measurements, and control. Control is both automatic control, because certain devices kick in automatically, and human element assisted by that. So what's the protective circuitry? Its basic job is to slow down or interfere with and arrest disturbances. You do that usually by tripping a circuit breaker to open so that the current can't flow any further. That has to happen very, very rapidly. It's got to happen faster than the disturbance can propagate. The risks are that if the breaker doesn't open fast enough, if it opens slowly or if it opens out of phase, the disturbance will get through before that happens. And if it gets to equipment like transformers and generators that are not designed to cope with that strong a disturbance or for that duration, you're going to have a problem. The problem will, as likely as not, knock that unit offline, or worse, it could cause it to self-destruct, possibly resulting in a devastating fire. In order for these circuit breakers and other protective devices to operate, some automatic system has to be taking readings on the status of the system so that it knows when a disturbance is starting. One of the disturbances that you want to watch out for is an imbalance in generation and load. What do I mean by that? There's no economic way to store electricity if you're talking about large quantities. So what do you have to do instead? You have to instantaneously generate electricity to meet demand as demand changes from moment to moment. On a hot day, if you know there's a heat wave coming, yes, you can schedule certain amounts of generation in anticipated expectation that we're going to need this much generation to meet that load. But the two have to be exquisitely in balance. You can't say, well, I think we're going to have a lot of demand today, so we'll produce a huge surplus of electricity. No, that would throw the system out of balance and the frequencies would go off and you would have a disturbance start to ripple through the system. Similarly, if there's a demand for electricity and it can't be met by the generation, you have that same imbalance and the frequencies in the system have to be maintained almost exactly at 60 hertz, give or take a small fraction. And as it goes up or down from that, the system has to adjust quickly to it. So if a generator were to fail, there would be a swift, steep drop in generation, and that would be a problem. And similarly, if demand were to slump, the same problem would occur. We'd have an imbalance. I put this character up because your system is basically supposed to detect when there is a disturbance, not in the force, but in the grid. Only unlike Yoda, this system has to respond quickly. You can't just sit there and say, I feel it, but I'm not going to do anything about it. So what's the monitoring circuitry? SCADAs report every few seconds, some of them even slower than that. That in today's grid isn't fast enough. So increasingly they're using phasor measurement units that do readings 1,200 times per second. That's pretty fast. That gathers the data. It then is put through some algorithms and produces certain measurements to inform people in the control room, this is the status of your system. And it gets time stamps so that we know what was the system doing at this time, and if it has a problem later, we can go back and learn our lessons. The aim is to detect disturbances as fast as possible, to start to counteract them, and if they start to propagate and spread, to be able to have things triggered. Now, maybe you want a protective device triggered. Maybe it's just a matter of restoring the balance between load and generation. So we may have to bring in generation from a neighboring part of the grid. Maybe we can't do that. Maybe the problem is we've got too much generation because suddenly there's been an outage someplace. Load has dropped, but it hasn't dropped enough. So now we have to do what's called load shedding, where you just deliberately cause an outage to bring things into balance. And you're going to hear that term repeatedly, load shedding. And I hope one of the things you'll get from this talk is some of that engineers' vocabulary for the grid. Load shedding, islanding, these shouldn't be mysteries for you by the end. An operator's constant thought is, what do I have to prevent from happening? Because at every moment, that's what their focus has to be. Disturbances can arise from an over or under amount of voltage, a loss of a transmission line as in a storm, transformers failing as they do. Many of these transformers are 40 or 50 years old and they're beginning to fail, but they also can fail if they're attacked, or as you can see from this, or if a disturbance gets into them and it isn't stopped in time. If there's that load generation imbalance I've been discussing, or if there's under or over frequency, or out of phase power, which is, for cyber purposes, one of the most important because if you can get power to be out of phase on either side of the transformer just near a generation plant, you can perhaps damage the transformer and perhaps destroy the generation plant, lose a big generation plant in a part of the grid, and it's going to be very hard for them to react in time to prevent cascading outages. Now, with all of that as background, knowing that the grid operates, knowing that it operates reliably because of those three kinds of circuitry, what makes it vulnerable to cyber attackers? Because we're not talking now about the typical cyber attack we've been reading about for the last 10 years. We're not talking about merely the exfiltration of information. And I say not merely because that is going on and is important for any adversary who wants to attack the grid, because the more they know about our security procedures on the grid, the more they know how our operators would respond to a problem, the more they know what can they do to confuse and frustrate and misdirect those operators during a successive phased attack. So what makes it vulnerable? Well, the grid's three circuitries are increasingly digital. Those are usually two-way communications, and if they're two-way communications, then they are going to be vulnerable to an attack. They're going to undoubtedly be run by software. We always know there's a certain number of zero-day vulnerabilities in this software. The question is, does the adversary have the determination and resources to spend to find that before we can? And remember that the adversary always has this wonderful advantage. They only need to find one gap in our defenses. We have to close all of them. That makes their task much easier than ours, and they may decide they're willing to spend the money on it. If it's linked to the internet, it makes it even more of a problem. Our nuclear power stations now have regulations that do not allow them to connect to the grid two kinds of information. Their cybersecurity plans for how they protect the place and how they would respond if there was a breach. Those operational systems, and in fact, the entire operational system itself is air-gapped, just to reduce the possibility of a cyber attack. But of course, air-gap doesn't mean that somebody can't take a USB stick, walk into the plant if they're working there, and a disgruntled employee, stick it in, and have the malware injection occur that way. But the more digitalization that we have, the more we keep rolling out the smart grid, the larger the attack surface is getting and the more attack vectors are being created. What will an adversary do looking at this? Well, it's a fairly simple thing for adversaries to write code to defeat protective circuitry and then to defeat all three kinds of circuitry. How might they do that? All they have to do is cause circuit breakers to close too slowly and out of phase. If they close too slowly and they're out of phase and the disturbance gets through before the circuit breaker can open and break that circuit, that's all that has to happen. And that doesn't require, apparently, from what I'm told, very sophisticated skills. What you want to be able to do, though, is know what part of the grid do I want to do that to. And that's why the reconnaissance efforts that you're reading about recently in the newspapers, where other countries are accused of and have been detected to be depositing code in our system and mapping out our systems, that's part of what they're trying to learn. Now, the worst thing that could happen to our grid is if an adversary made a coordinated adaptive cyber attack, trying to trigger what you could call a multiple contingency incident, where several things are going wrong, not necessarily simultaneously, but in rapid succession, so that the operators can't respond properly. First thing you want to do is to cause as many high voltage transformers to fail as possible, because that will be very hard to cope with. If you can get the sensors to misreport a status with a man-in-the-middle attack, where instead of them reporting that there's a problem, they're reporting everything's A-OK. That will cause the operators in the control room to fail to respond in time and to see reports of problems elsewhere as perhaps false problems. In other words, they start misbelieving the part that's accurate and believing the part that's false. The protective units might then operate too slowly. You get a load generation imbalance, goes on a wide excursion, and the cascading effort begins, cascading outages. There would be, in the case of that kind of an attack, a risk of generator damage. And remember that any mechanical failure in the generator is potentially volatile, highly dangerous. You could easily have an explosion. This would be particularly problematic if you've had a generation plant offline for maintenance, and then at startup, If you don't have those three currents in phase, you could have an enormous arc. Now, when I say an enormous arc, I want to make sure that everybody understands how large these things can be and how sustained. They're not just one instant, a quick spark. As this, whoops, that didn't work. Let's go back. I'm hoping that this will play. Here you go. Okay? These arcs don't just happen once. And when I talk about a disturbance that continues to flow and is flowing longer than the equipment can handle, that's a good example. It can melt circuit breakers, it can melt conductors. You can have, as a result, a high voltage fluctuation on the generator side, again, faster than any circuit breaker could respond to, and that would cause a fireball. Now, even more important than generators, and from a common sense point of view, what could be more important than a generator? That's where the power starts. Well, generators are easier right now, as long as the damage isn't too great, to replace a part of. But if we lose a high voltage transformer, the long lead procurement time for these is extraordinarily long now. This has been looked at recently in recent reports. Part of the problem is that no region has ever had simultaneous failures of heavy transformers, large transformers, and so nobody's quite prepared for that. They're not maintaining a large inventory of spares. These are vulnerable to both physical and cyber attack. Some of you may have read about the Metcalfe substation just outside Silicon Valley, which is the choke point for electricity going into the valley. Snipers attacked that about a year and a half ago with rifles at about 1 or 2 in the morning, and in a matter of 9 minutes knocked out 17 of the high voltage transformers. Had they not been able to reroute current around, the entire Silicon Valley would have been out for as long as that station was, and that station was down for 29 days. The wire wrap cores in transformers generate, as you would expect, tremendous heat that has to be dissipated somehow, and the way we deal with that is that it's cooled with circulating oil in tremendous quantities. Now, of course, that oil itself is volatile, so if the transformer fails, there is the possibility that the oil will ignite. The resulting fire is quite something to contain. Now, the second problem is if the transformer is that badly damaged and we can't just replace a few spare parts on it, how hard is it to really replace? Well, first, let's get a sense of the magnitude of these things. A high voltage transformer can weigh up to or more than 400 tons. It will have inside it upwards of 30,000 gallons of cooling oil. So they're large, they're heavy. The bigger they are, by the way, the more voltage they can step up or step down. But what's particularly problematic is that they tend to be unique to the substation, both in their physical dimensions, in what they're supposed to be able to do, and they are made to custom specs. So you can't go to some local dealer who has an entire showroom of the same kind or a warehouse filled with these. They are often not built except to order. And the procurement process is intricate. It's long, especially since it has to go offshore. And to give you a sense of the differences, since a lot of these are no longer made in the United States, a study that was done back in 2010 found that in the U.S., the lead procurement time is 5 to 12 months for any of these. For the foreign made, which is where most of them are, it's 6 to 16 months. And that can stretch from 20 months to 5 years for certain key parts which might not be available, or if the ore that's needed to make them is suddenly in short supply or some country is cutting off the supply. U.S. manufacturers in 2010 made only 15% of the number that we needed at that time. So that should tell you why the figure of how much is coming from offshore is the one that really determines how long a severe event should be anticipated to last. Destroy the transformers, and we're looking at least 6 months, possibly 16, possibly much longer. Now, what if we've got the purchase and seeming delivery problem solved? Well, yeah, we'll put it on a ship, we'll send it here, but now once we get it to a U.S. port, how do we get it to the plant? You can't throw it in the back of a pickup truck. It's too heavy for that. Transporting it is challenging because of the size and weight. You also can't stick it on a normal freight car. It's too heavy, and freight cars have certain things. They've got to be able to go downhill. You can't do that with something this heavy on a normal freight car. They also have to be shunted together in the freight yards. Well, that kind of banging together on a normal freight car would cause damage to a transformer. So instead, they are put on something called a Schnabel car. This is a Schnabel car. Most of you who have electric trains will not have a car like this, although I'm told that somebody's now making them. Look at the number of wheels on that side of the car and on that side, and there's your high voltage transformer in the middle. There are only 30 Schnabel cars in North America. So if we needed to move a lot of transformers, getting the Schnabel car in California into the Northeast would take some time in itself. And then the question is, who's going to get it first? Who's booked for that train in that severe event? Now, is a severe event from a cyber attack really a credible risk? The estimate of how credible it is and how serious the threat is has been going up ever since about 1990, when we had this study done that said the destruction of more than 3 transmission substations would cause long-term blackouts. Well, we've read things like that a lot in the newspapers. This is a very credible source, but the United States didn't rush out to deal with the problem because it still wasn't viewed as a very likely event until the Aurora test. The Aurora test was something that was done at the Idaho Laboratory at the request of the Department of Homeland Security to find out, can cyber actually cause kinetic damage to critical infrastructure? And what they did is they injected malware, they caused circuit breakers to open and close, eventually out of phase. That damaged the alternating current equipment in there. And to look at what actually happened, they made a video and watch what happens. First, the machine starts to experience the disturbance as a jolt. Then the jolt becomes a disturbance inside the machine, and eventually it causes it to self-destruct. There's that first jolt. This is a generator. But this was just with cyber, just by getting the circuit breakers to open and close and to cause that disturbance. So that was the theory, but then it got put to the test, a proof of concept with STUXNET. STUXNET was to target SCADA using Siemens software, and in particular, SCADA systems located in the enrichment facility in Iran at Natanz. This was an extraordinarily sophisticated piece of software. It probably was injected into their networks with a USB, though I simply don't know for sure. This is speculation. But what it actually caused is remarkable. First, it caused certain centrifuges that were, because there's the way you enrich uranium is you put the stuff in this centrifuge, you have these elongated centrifuges spinning at very high speeds, but they have to spin at within certain manageable conditions. Not too fast, not too slow. It sounds like the story of the 3 bears. You know, there's just right and nothing else. And what it did, it didn't cause it to suddenly accelerate and fly off someplace, because if that had happened, the facility would have realized somebody's doing something, somebody's trying to sabotage us. Instead, it would cause it to go too fast for a few minutes and then slow down and go normal. And then a day or two later, it would cause it to go too slow and then come back to normal. And gradually, over a period of weeks, it increased the fatigue on the system, so its MTBF collapsed, and basically you had it fail much sooner than it would have otherwise, but not so rapidly that people could think it was being sabotaged. Instead, they thought the operators weren't handling things properly. Over and over again, this became a problem. In the meantime, it also did something else. It adjusted the power supply, raising the pressure inside the centrifuges to cause them to do emergency dumps of the precious uranium gas. So that would be wasted. And then it did something else in addition. It kept reporting that the system was A-OK with a man-in-the-middle attack, basically impersonating the data from the SCADA systems in the plant telling the operators things were fine. And that, of course, made even further problems, presumably, when their supervisors came in and said, this is broken, why weren't you watching it? We watched it, it said it was normal, you can see the amount of effort that went into it. The only problem with a STUXNET is once one country uses it, or two countries or three, however many were involved, it's out there, and others will then find ways to replicate it. Now, in 2013, FERC did a study. It was not meant for public consumption, in which they determined that if you could destroy 9 interconnection substations, just in the Eastern Connection or the Western, and a transformer manufacturer, the U.S. grid, the entire U.S. grid, would be down for at least 18 months. FERC is not in the business of producing rumors. They're a very serious federal agency. They didn't want this published, but about a year later, it was published in the Wall Street Journal, and one of the commissioners came out, criticized the journal, saying the publication of other sensitive information is highly irresponsible, and while there may be a general value to having this kind of discussion, publishing this is very unhelpful. They wanted to say much worse, and they probably did in private. Then, in February 2013, DHS's Inspector General released a report saying a recent survey showed that a majority of companies in the energy sector had experienced cyber attacks. 55% of those focused, targeted the industrial control systems. They also found that a successful attack on such a system could result in damage and cascading effects that could disrupt services, exactly what we've been talking about. But in looking at this, understand that they're concentrating on the fact that most cyber attacks on the grid would attempt to exploit an internet-facing industrial control system. And as we roll out more of the smart grid, we're expanding those kinds of systems. We're not reducing them. So, how are we reacting is a little puzzling. Cyber attacks have also been warned by the DHS. DHS has told various energy companies in confidential releases that came out back in May of 2013 that adversaries are seeking now to disrupt the control processes in your companies. Not the business information, the operational side of it. Lawyers for those companies were not allowed to see the notices. That's how sensitive the information was. All we got was a sentence or two, and that was about it. A study on the vulnerability in the grid done back in 2011, what's interesting is to see how many of the vulnerabilities involved either supervisory control access or SCADA functionality access. More recently, back in October of this year, late October and early November, DHS released an alert warning that a variant of the black energy malware had been infiltrating the human-machine interface products via the internet in the energy sector in particular, and had compromised numerous ICS systems. And that it had been going on, they now believe, since 2011. Why did they wait that long to deliver the alert? Because nobody knew it was there. That's another element of these cyber attacks, is that if they're sophisticated and well-designed, like STUXNET, they're stealthy. STUXNET went on for years before it was identified and could be eradicated. Now, I mentioned at the start yesterday's testimony by Admiral Rogers. Look at how it got reported. NSA director warns of dramatic cyber attack in next decade. What he really said was he thought it increasingly likelihood that it was going to happen. He said, we are observing intrusions into our control systems. And he added, it's only a matter of when, not the if, that we are going to see something dramatic. Okay? I much prefer to look at that than the headlines. The headlines I find misleading. Now, as a result, this morning it was reported that yesterday FERC released a new rule to the companies that it regulates. Remember, since it's a bulk power regulator, this is to the generation and transmission companies, that they must now go out and identify key transmission substations, make sure they're adequately defended, and bring in unaffiliated experts to review it and verify that the protections are adequate. Now, if we're assuming that this threat is credible, and it seems to suggest that it is, how will grid operators try to respond to such a cyber attack? In fact, NERC has been thinking about this for quite some time. They assigned task forces to work on this right after the high-impact, low-frequency study was done. And they produced their reports, and their board of trustees adopted these back in May of 2012, which was about 9 months before the president issued his executive order on cybersecurity. They did one on how the attacks would happen, and they did the other on severe impact resilience. The severe impact resilience one was actually the more interesting. If you put the elements of those two together, here's how an attack would sort of run. And I'm going to put on the left side what the adversary would do, and on the right side how the grid operators would perceive what was happening. The adversaries would probably try to cause a circuit breaker reaction where it's too slow and a disturbance could start to enter, protect critical units. So in the control room, what they would see is displays showing unexplained and persistent breaker operation. They're not told what's going on at that moment. Remember, like the submarine, all they know is what the data is that's coming in, and we're assuming at this point a man-in-the-middle attack hasn't started, so they're still able to at least rely on the information they're getting. Now the attackers start to develop a load generation imbalance. They do that by disrupting generation units and high voltage transformers longer than they are designed to handle that kind of disruption. Well, what would be seen in the control room is a loss of load in one area, a loss of generation in another, disturbances propagating, the grid rapidly destabilizing. At the same time, the adversary, without much effort, would be able to trigger interference with their telecom links. Now, all of these have hardline links. That's what they would attack first. They have SATCOMs. That would be the one that would be the most protected and the hardest to attack. But communications that they normally would rely on would be disrupted. They would lose voice and data, probably with half of their neighbors, according to NERC. They would then lose contact with their reliability coordinator, and most importantly, with the balancing authority. That authority which decides, are we going to add generation? Are we going to shed load? How are we going to get this balance back? Then the adversaries might launch an adaptive attack. Direct monitoring circuitry now to start sending false reports. Because the operators are trying to get things stabilized. The worst possible time to have the false reports come in is not at the beginning, but after things have really started to break down. Their corrective actions might well have the opposite of the intended effect and aggravate the situation rather than stabilize it. The imbalances would widely fluctuate. Under frequency load shedding, automatic units would kick in and start kicking things out. The grid instability would grow and spread, and you'd get at least some islands beginning to form as areas began to go down. The adversaries might then intercept and review the operator's inputs and efforts to communicate so that they would know, well, this is what they're trying to do to restore it. Here's how we'll try to interfere with that. They would also probably try to wipe system logs to the extent possible and other traces of intrusion, because the longer they can disguise what they're doing and that anything cyber is at all happening, the greater the impact. And they also want to try to defeat the forensic effort that is inevitably going to happen at the end. So they're going to try to disguise or conceal evidence of the attack. The operators eventually are going to lose their situational awareness. There'll be a large section of the interconnection would collapse, and you have basically blackouts. Islands would remain, but load shedding would be required to keep them stabilized. The operators would strive for what they call graceful degradation, meaning you're trying to fly with fewer controls and keep things stable and bring them down to some place where we can get at least a semblance of order. Some islands where we can say, all right, there we have power, we can build from that. But if this keeps going, the number of those islands that you can keep stable or keep stable with anything that's on schedule so that the customers know when they're going to have power and when they won't, will become increasingly difficult. Eventually, the confidence in the protective and monitoring controls is going to be lost, and the operators will, of course, inevitably start to doubt themselves and what they're doing. From their perspective, for all they know, what's going on out there is Godzilla's attacking their high voltage lines. But of course, by this time, somebody will probably, with all the attention that it's been given, start to recognize this may in fact be cyber related. So the grid starts to break up. You might have multiple transmission lines failing. Innumerable islands would appear. Rolling blackouts would be needed to stabilize those. And from now on, the grid would be operating at a reduced state of reliability under completely unfamiliar conditions with uncertain supply and demand. It would take the operators far beyond any of their emergency procedures that they're used to working on. They have some that they've developed for storms, for hurricanes, for earthquakes with limited impact. But when you're telling them you now have to work with an entire interconnection with scattered islands, and you won't know what part of it you're responsible for, and you're going to have reports on stability coming in manually from the field, and by the way, this may last for months, they don't have plans at this time for that. Their standing orders, which they all have for what they should do in a crisis, would rapidly obsolesce. And you are now into the new normal after a severe event of at least 6 to 12 months or more. The operators in that period of new normal would be trying to figure out who gets critical, who are the critical customers, first responders. We've got to make sure that they get power to the extent that we can move them into an area where we have some. Then the priority loads. Now, if you're running a business and you're not a first responder and you're not a telecom and you're not part of the critical infrastructure, but you're trying to run a company, you've got to be concerned about where you are in this schema of their plans. And if you don't know that as engineers, when you form your companies, this is something you ought to find out because you're going to be completely dependent on the supply of power. The grid operators, one of the things they're going to be doing repeatedly is inducing load shedding to stabilize that island. But they want to make sure when they do that they don't cut off power to their critical or high priority customers. And sometimes they're going to only be able to provide to the critical and not to the high priority. And they're going to try to do it on some kind of scheduled outage, the kind that I experienced in England during coal miners' strikes, where we would be 4 hours on, 4 hours off, and then we had to move to another part of town because we didn't know where the third unit of power was going to be, and then we could race back to the original library for the last part of the day. Crews at this point would be coming back to the operators reporting the on-site inspection of the generators and transformers, confirming that these are irreparably damaged. And now imagine with an already intricate procurement system trying to order and get approval to order and getting the funding to order these critical parts from offshore. That's not going to happen in record time unless you've got standing orders already online with suppliers, and you first have to find ways to communicate with them. So I'm now going to just tick off a few of the other kinds of problems the operators would have during the new normal period. They've got to stand up a new control center, and they got to hope it's in one of the areas where there's an island. If they put it too close to their original center, their backup center is going to be in the same condition. There'll be limited situational awareness throughout it. They probably won't have the internet. Their emergency supplies are probably going to run down because food deliveries and other deliveries are going to be compromised, especially if fuel deliveries have been compromised. There will be conflicting authorities, and this is going to be probably the worst part because, remember, the distribution people aren't covered by the federal government. The Department of Defense isn't responsible for protecting the grid unless the president orders the Department of Defense to go and protect critical infrastructure. But right now, they're still trying to figure out when would that be triggered. And the power companies don't know, so they're not sure who they're supposed to be taking orders from, except that they know that they are now, in effect, defense contractors. Why? Because they're on the front line responding to this attack. They're the ones responsible for restoring power, and they're the only ones really capable of doing it. They're also going to have to be trying to figure out forensically what actually went on. They're going to be trying to use that to help them remove the malware. And as they start to restore the system, they have the supreme challenge of black start operations. You can't just flip a switch and have a generation plant start. You've got to get power from somewhere else usually to get that plant going. And that would be difficult in an islanding situation. Now, would business deals survive a severe event? I don't want to ask this in the abstract. And so in a part of a conference that I was in New Delhi back in February, that was on cybersecurity in the grid. We gathered people from Tata Power, cybersecurity community in India, room full of lawyers of about 120 lawyers, some American lawyers. And what we did is we set up a scenario. And what we wanted to find out is as we ran that scenario forward without any rehearsal in advance, would we be able to find a way to keep the deal intact? Or would our various cultural approaches to the law, cultural approaches to doing business, and our understandings of our respective grid cause us to misperceive and misunderstand each other in a way that would drive our deal towards breakup instead of keeping it intact. And unfortunately, it did get rather dicey. So here's the scenario we ran with. We had a buyer in India. The buyer is called Reliable. Reliable is based in Bangalore. They make navigational control systems for high-altitude platforms. Think high-altitude aircraft, low-orbital satellites. They have a critical parts supplier in New Hampshire called Omniscient. Omniscient is based in Portsmouth. By the way, this is, of course, fictitious. They make inertial switches. Those detect shocks and activate safety shutdowns. Now, they negotiated what's called a just-in-time supply contract, meaning instead of sending a forecast, you want rolling forecasts so that they will always have whatever they need just in time, so they don't spend a lot of money having stuff sitting in inventory. So as they keep seeing their demand going up or down, they send forecasts out 3 or 4 months in advance, and at the 1.5 month point, it becomes a fixed order, because now that looks reliable enough. All right, so that was to be made for multiple years. They made the governing law in New York, not New Hampshire, not India. Why? Each one decided they wanted their own law, and they compromised on a sophisticated jurisdiction, New York, which is commonly done. That's how New York lawyers in part sometimes make a living. Reliable issues, as I said, these rolling forecasts, and in this case, they would become binding 1 month out. Now we're going to start a timeline rolling, and it's also going to play upon the fact that the president issued his executive order. Under that executive order, the Department of Homeland Security is now authorized to send out 2 kinds of notices. They didn't give them a name, so I've coined a name in the article that I gave you a copy of. One kind of order says, you're such an important part of our critical infrastructure that if you are ever damaged, the damage economically and to our national security will be widespread throughout your region. The other kind of notice, very confidential, very sensitive, will say that we now believe an attack on the U.S. homeland is imminent and you're one of the targets. What's important is that whether you get one notice or the other or both, you can't put them in a drawer and ignore them. You're now on notice. You can't sit back and say, I did nothing, I didn't think this was foreseeable. Your legal defenses to inaction are being stripped away from you by your very helpful federal government, responding to your desire to have more intelligence about the existence of cyber attacks. So imagine we're in January 2016. DHS sends out to Omniscient a catastrophic target notice saying if you're damaged, there'll be huge effects in your region. Then in July, they say, we think that an attack is imminent and you're one of the targets. A few weeks later, they sign this new contract without ever telling Reliable that they had received these notices. There was no cybersecurity assessment back and forth between the parties. They just trusted one another. Shipments begin. A major snowstorm, surprise, surprise, occurs in November. And it happens that year to be early in the month, 2 days before something very distracting, a national election. The adversaries have been waiting for precisely this concatenation of distracting things so that everybody is looking somewhere else and nobody wants to be thinking about my deal or what's happening on the grid. Everything would then just be perceived as a terrible inconvenience. So the kinetic cyber attack begins, it targets, and in a matter of minutes, it's brought down the Northeast interconnection. In the initial days after that cyber attack, it wasn't detected as such. The islands of electricity are there. There's rotating blackouts. But more than 50% of the total instantaneous demand in any given island can't be met by the limited generation sources. So what's happening between the two companies? Well, Omniscient is silent. Why? Well, they don't want to tell their buyer that they're having problems, and they don't know how long the grid is going to be down for. They're trying to get information from their local grid operator, who's swamped with orders like that. They're not on the high priority list, so they're getting the silent treatment too. But nobody knows at this point that it's a cyber attack. Nobody knows how long this will be out for, and the president is trying to make a decision. Do I tell the public how bad this is, or do I make them comfortable and not panic them while I roll out units so that I can declare martial law at the appropriate time? So as a company, you're in the dark. You don't want to tell your buyer. Reliable contacts Ohm and asks what the status is, but they don't contact them by phone. Why? Because the Indian company waited too long. They thought, from their experience with their grid, which is very rickety, goes down several times a day, in any hotel you're in, in a talk like this, the power would have gone out at least once or twice. It kicks back in as the generators start up. And after 45 seconds to 90 seconds, you're back with illumination. In the meantime, nobody stops talking. Everybody just goes on. Even though it's totally dark, nobody gets up and says what's going on. They just continue their meeting. And so they thought, that's how our grid operates. Our grid is not very robust, but it's very resilient. It bounces back. The American grid must be that way. And they told us, that's how you guys dealt with Sandy. You were back running within a few days. No, 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 no. South of 39th Street in Manhattan, we didn't have power for 2 weeks when that substation went down. Impossible, the Indians said. They hadn't read about it in their papers. They assumed that we did like they did, that we had generators in all of our important facilities. No. So they're thinking, reliable will come back. And finally, when the silence went on too long and they began to read reports from other newspapers and other sources that this thing was going on, they tried to contact them by phone, but by that time, Omniscient's cell phone batteries were gone. And some of the telecoms were collapsing. So what they did is they hired a courier in Canada to drive to New Hampshire and find out on the spot and then drive back and report. And to make sure that they had enough fuel because they might not be able to refuel along the way. Then they asked their counsel, the American company did, Omniscient, hey, maybe we should declare an act of force majeure. That's a fancy legal expression, meaning an act of God or an impossibility of performance. And you send it and you're basically saying, we want, because of this thing beyond our control that wasn't our fault and that we weren't negligent in trying to respond to, we should be excused from further performance and shouldn't be punished for it. Well, that's not what the Indian company wants. They're used to the concept of jugaad, which is you make do, you're resourceful, you find ways to deal with things, the sort of can-do. Where's this American can-do attitude? Well, the Americans are getting very legalistic advice, so they're just thinking about protecting themselves. The Indians instead offer to relax performance. Hey, we'll give you a longer delivery schedule. You don't have to deliver so many units. Let's keep this contract rolling. The Americans are saying, they're just trying to trick us. They mistrust the offers of goodwill coming to them. And so eventually they send them an email saying, we're declaring an event of force majeure. The Indian company looks at that and starts asking questions. Hey, were you notified by your government that a cyber attack was imminent? Because by this time, finally the word is out that it was a cyber problem. Did you have very good cyber defenses? What have you done to make sure that you'd have power knowing that this was coming? And finally, they send the American company a fancy letter under New York law which says, we want an adequate assurance that you are going to fulfill your obligations. If they can't give an adequate assurance, they're in immediate breach. If they give an assurance and then don't meet it, they're in breach. It's kind of a, you're damned if you do and you're damned if you don't letter, and it's a very powerful legal device. And that shocks the American company into saying, maybe we're not on such strong ground. And finally, the Indian American counsel tells them, by the way, your force majeure clause, it doesn't mention Cyberattack. It has a whole list of acts of God. And under New York law, since you list all of those and you didn't list cyber, then cyber is construed to be not included. And that's the way most force majeure clauses are today. So this is a terrible situation. A number of lessons we realize, those clauses need to be updated. Boilerplate needs to deal with these things. You've got to start thinking about what's going to happen with these DHS notices as they arrive. But more importantly, we've got to put into our contracts more flexibility so that we can assist the non-performing parties, have methods for communicating in advance of these crises. It doesn't cost a lot to say, hey, let's spend a couple of hours talking about how we're going to survive if a cyber attack, which is now in your newspapers a lot, your own Director of National Security has said this is likely, why don't we start talking about this and developing standing orders to deal with it? Now, 3 caveats to this entire presentation. First, to date, have cyber attacks or squirrels caused more grid damage? How many think cyber attacks? How many think squirrels? Clearly we're in New Hampshire. You know your squirrels. I also am informed that over the last 3 evenings at 6:30 p.m., power has failed in the Hanover area. Now, if it had failed once, I would have thought squirrel. If it had failed twice, I would have thought an organized den of squirrels. But 3 times, I doubt that the local squirrel community has such precise circadian rhythms that every time they go into the power station, stand up, make the connection, commit suicide, and bring down the local grid. But I can assure you it's not happening for no reason at all. Now, how often do squirrel outages occur? Well, let's look at October 21st, 24th, and 31st this year in the Northeast alone. Well, we had Providence go down, Northampton go down, and Lewiston, Maine go down, all to squirrels. And in the 2013, 50 outages across the country to squirrels. If the squirrels were ever to organize, they, rather than a cyber adversary, could bring down the grid, clearly. All right? Second, national economies in our digital era really are incredibly dependent on this seemingly reliable but very fragile grid. And let's look at the impact of it. And if you want to see the importance of what we've been talking about, start looking at how this is affecting other nations. Pakistan has a population of 180 million. They can't generate as much electricity as they need. They're a good 6,000 megawatts short. California generates 60,000 megawatts with a much smaller population. Power shortages, which you have to understand, create a pre-industrial world. In Pakistan, the high-powered textile companies that bought lots of machinery so they could produce at high quality, high rate about 8 to 10 years ago, thinking that their grid was going to be able to handle the load, are now being reduced to operating at 2 to 3 hours a week. It is very hard for them to even pay off the debts on the machines, let alone make a profit in that kind of environment. But remember also, their population in the areas where they don't have power or where it goes out, no fridge, no light, no heat, no air conditioning, you can't recharge those digital devices, and, as I said, limited industry. And this has been widely reported in our press, though people tend not to read those stories. In India, you have 300 million people who have limited or no access to power on an ordinary day, not counting the number of times that their grid will go down. Their power plants operate at only 70% capacity because they lack enough coal. So what's their new government doing? They are now going to increase the amount of coal that they're going to mine. Of course, coal increases global warming. Global warming will make things even harder on those low-lying Indian communities as the oceans rise and as the snows melt in the Himalayas, and they won't have as much hydroelectric production. So this gets to be a very vicious circle quite rapidly. How bad can it be in India? Back on July 30 to 31st, 2012, half of the country was suddenly without power as their grid went down one day, came back up overnight, went down again. That's a very sizable proportion that gives you just a sense in their country how it could happen. Bangladesh on November 1st, their entire grid went down for over 24 hours. Entire country blacked out. So these things are happening with a greater frequency, and they're causing ancient enemies with great animosities to cut remarkable deals. The Indians don't have enough power for themselves. The Pakistanis have even less, and the Pakistanis are now entering into negotiations and have been negotiating for quite some time to join their two grids so that Pakistan can buy power from India, even though they know that that will put India in a position of great leverage if they do that, because if the Indians didn't want to cooperate with the Pakistanis on something, they could say either do what we want or we may suddenly cut the power. But it's that important to Pakistan that they want to do this, and it's that important to India that they would like to see this move forward. Third caveat, the reliability of certain cyber defenses is continuing to erode, especially air gapping. Now, I don't have any inside knowledge on this, but these news reports, which came out 2 years ago, said that the DoD was developing, or already had developed, or was doing something to jump the gap and could now load malware without having internet access and without sticking a USB into the port. I don't understand how it would happen, but it begins to make you think that one of the ways to get defense in depth isn't to add more equipment, but to avoid certain new technologies, especially if they don't have cybersecurity designed into them. And clearly, digital technologies got deployed to the grid before cybersecurity was taken seriously. Certainly at a nuclear power plant, they're not allowed to have wireless technologies connecting to their operational systems. No internet connection, no open ports for USB. But that doesn't address the supply chain and software problems of microprocessor chips that might already have malware on them, and you can't always scan accurately for them. You could also get further protection by reverting to obsolete software and pre-digital technologies. Is that far-fetched? Not if you're in Russia. After the Snowden disclosures, the Russian Guard Service went out and ordered a number of Triumph manual typewriters for their top-secret communications. No way to digitally hack those. And as long as you're not using a ribbon that you only use once, be very hard to decrypt it. At the end, let me just sum up by saying cyber defenses have been porous. They're getting even more so because of the rolling out of the smart grid and the increasing sophistication of the advanced persistent threats. Malware, you should assume, has already been planted in the grid circuits. Severe events, if they occur, if an adversary chose to launch one, would return that region to a pre-industrial age. So the questions I want to leave you with is, are there corporate cyber responsibilities to respond to this? I think there are, and I think boards of directors are increasingly going to have to address those, or their stockholders and investors will start asking some very serious questions. If so, I think those corporate cyber responsibilities surely include preparing to recover from severe events, and engineers will be the most crucial players in developing those plans because they will know what can go wrong, they will know what's the most efficient way to deal with it, and you're not buying equipment, you're asking them to sit in a room with various other people and to think through the problem about how they would respond, and to do it at a level that, let's say, the U.S. Navy does when it rehearses certain things. When they're doing damage control, and I don't mean spin for publicity, but when they're trying to respond to damage on a submarine, they first train everybody on what they should do if a compartment starts to flood. Then, having done that, they go into the compartment and they declare that certain people have been injured or are unconscious and are unavailable. Now, run the drill the same, but the people that they've taken out are the ones who were giving the orders before. The crew has to now know how to act without getting orders. That's the kind of preparation and rehearsal you need. And that's the kind of care that this deserves. And I would encourage you as engineers to consider not only is that an opportunity for you of something that you can bring in value to the companies that you create or join, but I think you have an ethical obligation for that, because engineers have an ethical obligation to be concerned about the safety of systems that they are either building, maintaining, or repairing. You've been a very patient audience. I'd be delighted to take questions for as long as you want. Thank you.